Hi, thank you for coming to this session. This is talking about the third version of the Cloud Data Management Interface, which is specifically designed to allow standardized management of any URI-accessible resource. So, to start out, why are we here? Well, we're here because of the convergence of three different waves. The first wave is the object storage wave. This started in the early 2000s. For example, AWS introduced S3 in 2006. But this also built upon big data, data lakes, and ultimately the integration of object storage as a primary data access mechanism into storage systems across the board. Not just in cloud, but also in on-prem systems, specialized applications, and client software that integrated object storage as a native means to access data. The second wave was the cloud wave. This has had various forms over the years. This goes all the way back to data sharing systems in the early 60s and 70s, but the current version really started in the mid-2000s as well, with the release of AWS, followed shortly by Google's cloud platform and Microsoft's Azure. We then started to see large-scale deployments in the cloud, which led to the concept of born-in-the-cloud architectures. These are software architectures that are specifically designed to run with cloud computing assumptions, instant availability, dynamic provisioning of resources, scale from nothing to very, very large infrastructure and then scale it back down, capabilities that you can't do on-prem. And as these resources became available and people understood the technical capabilities and limitations, the economic model, that enabled new ways of building software systems that weren't possible before. In an on-prem environment, a data center environment, you couldn't spin up 10,000 cores for an hour. But you can in the cloud. In fact, it's relatively economical and a great way to solve problems that were very, very challenging when you had a fixed number of cores that were always busy doing things that you didn't over-provision because that would be very expensive. But in the cloud, it's cheap. So this resulted in new architectures, new ways to develop software that really opened up a whole new set of what is expensive, what is cheap, what is easily accomplishable, what is difficult. And now we're in this third new wave driven by AI technologies. This really launched onto the stage in terms of visibility with ChatGPT, but it's been developing for many, many decades. It's only now just started to fulfill some of the capabilities that have been predicted for a long period of time. So what big changes has this AI wave caused in the data storage space? Well, first, there is an explosion of a requirement for training data. The better the data, the better the model. The better the model, the better the processing capabilities. When people were able to build these models and then run inference to actually accomplish things, make predictions, complete text, make decisions, etc., they started building inference into everything they could think of. Many, many good ideas, some a little more dubious. Did it really make sense to put inference into that? But it's providing value, it's providing differentiation, and now we're starting to see the next step, which is agentic AI. The concept is not just generating an answer, but using AI as intermediate steps in reasoning and being able to solve larger problems and being able to incorporate other parts of the system. Just like we went from very simple computing models where you'd have a function that you call and get back an answer, and then you start combining those functions to build larger software systems. Agentic AI promises to open up new ways to build software based around AI technologies. And of course, like any new introduced technology, it goes through a period of time where we're trying to figure out what it does, where it makes sense. And of course, it gets a little overinflated. People promise that it will do everything. And then we figure out, well, maybe it doesn't do everything. It does these things really well, and it does these things not so well. And we start to identify exactly where it's best to use. For object storage, we're well along this path. Everybody understands where object storage works well, how it fits into the existing technology stacks. There's a little bit of debate still on the edge. When should you use a file system? When should you use an object store? They're overlapping. Most file systems nowadays have object store overlays on top of them. Most object stores have file system overlays on top of them, and you could interact between the two of them. Similarly with cloud. There's an understanding of what cloud does, when to use it, when not to use it. There's still some people pushing applications that probably shouldn't be in the cloud and pushing applications in the data center when it really would have been better to do it in the cloud. But this is now generally understood. In AI, we're still in the early stage. We don't quite know where things are going to land, but we know, just like with cloud, things aren't going to be the same they were before. So what does this mean for this talk? Well, this data explosion is continuing to accelerate. Not only are we needing more and more data to make AI have value, AI technologies are generating more and more data. And this is making data management more important than ever before. So, how is this changing the traditional data management use cases that we've worked with for the last decades? Well, the first thing is, you don't have any data, you don't have any AI. The LLMs require data, the LLMs generate data, agentic AI is going to make this even more so. You need this data for and generate from your AI experiments. How am I going to make this work, fine-tune it, refine it? How am I going to benchmark the systems to know how well they're working and that they're working economically? How am I going to do my training and run my AI inference? And these next generation AI technologies, agentic, world model, physical AIs will require even more data. This has to all be actively managed. This is causing a trend towards data sets. If you're managing billions, trillions of items of data, it's just too complex to manage them at the individual level. You have to organize this data into sets of data that is managed together. And that's one of the big trends, formally managed collections of data. And this is difficult to do manually, but AI can solve this problem very well. Create and identify these self-describing sets of data. And we're seeing this in many different places. We're seeing the concept of the data asset that's recognized from a financial standpoint, just like you might have a factory or a ship. And that counts on your books as an asset that depreciates, that has value. And if you're acquired, it's part of the purchase price and you can get insurance for. The financial folks are looking at data the same way now. The data asset has value. And if you can identify that and manage that, it links your costs with your value. This is very important. The financial guys drive a lot of what we do. They pay for what we sell. So this is a big change. And you have to somehow be able to discover this. The rise of data catalogs provides a mechanism where within your organization you can say, oh, this is the data I have, and I can search for it, and I can find it. And I can understand how it's used and what value it can provide. And I can share it. And I can look at other people's catalogs and public catalogs and use that to determine what I can build by connecting these data pieces together, like Lego bricks. In addition, there's requirements for reproducibility and traceability. You have to know where the data came from, what the legal requirements are, what the restrictions are. You need to be able to reproduce it in the future. So you want to make sure that if I trained a model on a data set, I can go back and I can find out what's in that data set and prove that that hasn't changed. This requires lineage. Where did the data come from? It's everything in conformance with the license. Provenance. Is this being managed? Is this being following the rules of use, etc.? And there's aspirations for portability across systems and providers. For example, there's a large project in the EU called the data spaces. The concept that you can take these data assets and these data catalogs and extend them beyond the enterprise to create mechanisms by which sharing relationships, purchasing relationships, supply chains for data can all be constructed. Company B buys or licenses a data set from company A, adds value to it, provides that as a derivative data set to a third company that then uses it. Revenue flows back. All of these new types of arrangements that we all know and well with physical products. But this is emerging in the data world as well. And all of this is going to be data that does not stay in one place, that needs to be managed through its lifetime. These new AI systems are often built using cloud technology stacks and cloud concepts such as Kubernetes and microservices, even when they're built on-prem. In fact, when we look at today's enterprise systems that you install in your data center, a lot of them look an awful lot like cloud technologies. In fact, some of them are pay-as-you-go. You may not even own the components that sit in your data center and run in your on-prem system. You may be able to burst up and burst down, and the software architectures you're using may be able to move back and forth between cloud and on-prem based on the economic requirements and your business needs. So even though we talk about cloud data management, this is becoming just data management. And finally, with projections that 85% of the AI deployments are going to be hosted in cloud service providers and other hyperscalers, this means data is going to have to move. You're going to build it in one place, move it to another place, deploy it to a third place. So this becomes very, very important for the use cases that drove the creation of the cloud data management interface. So, why does the cloud data management interface exist? Well, there's many, many different data access protocols that are used in cloud environments and on-prem environments. For example, in the file category, we have NFS, we have SMB, we have FTP, we have new technologies. A lot of people use Google Drive to move data around. A lot of people are looking at newer improvements, SMB Direct, NFS over RDMA, etc., to accelerate data movement on-prem. And now this is starting to move into the cloud as well. In the object world, we have, of course, HTTP, which we could argue is the original object storage protocol. We have S3, we have Azure Blob, Google Cloud, storage objects, and many, many others. And just like the pressures with file world to use these accelerated fabric conic protocols like RDMA to accelerate in the data center, we're seeing work starting here in SNIA for S3 over RDMA to standardize that. And of course, we can't ignore block. Block is often the foundation for many, many use cases. And that is found not just on-prem, but also in the cloud. NVMe over Fabric, iSCSI, even Fiber Channel Protocol is still being used widely. And now that we start to get into some of these born in the cloud, cloud-native architectures, we see stream protocols, Kafka, AMQT, MQTT, ways to tie together loosely coupled dynamic streams of data processing. And database queries, of course, SQL, Postgres, Sparkle, GQL for graphs. Databases technologies are experiencing an explosion of new applications as they are deployed to provide value and augment and enhance AI technologies built around LLMs. But there's an issue here. When you have all these different protocols, they're each designed for a specific purpose. A block protocol is designed to give you block access. It's not designed to do database queries. A file is designed to access named files within a hierarchy. It's not designed for stream notifications. So each of these protocols are designed to express the concepts within the scope of that protocol. You can't describe concepts outside the protocol from within the protocol. So this means it's not possible to manage data access across protocols from within the protocols. But data access across protocols is what we're increasingly doing. In addition, the cloud management protocols are specific to each cloud. There's protocols for managing your cloud infrastructure when you're in AWS, when you're in Azure, when you're in Google Cloud, when you're in other private cloud environments. But The problem is that you can't create, manage, and export data in a standardized way. There isn't an abstraction or an overlay or a mechanism by which to do that. And these protocols assume that data stays within a cloud. There hasn't been a standard way to move and access data across clouds in a portable way. And these three items are why CDMI exists. The Cloud Storage Technical Working Group started up in SNIA in 2010, and we identified what gaps were there. And many of these gaps still exist, showing that the value we provide through this standard is enduring. So what's CDMI's mandate? Well, CDMI, the Cloud Data Management Interface, also known as ISO IEC 17826, because this is now an international standard, provides a vendor-neutral standard interface for multi-protocol discovery, configuration, management, and portable data movement. Implementers consider CDMI for applications when they require protocol-independent data management. And CDMI allows clients to use a lightweight and consistent management interface that operates independent of the data access protocols. By enabling these management operations to happen outside of each specific data access protocol, CDMI works across multiple data access protocols and multiple deployment models, including on-prem, hybrid, and cloud deployments. So if we look at the four key capabilities that I mentioned earlier, the first one is discovery. What's out there? How can I find out what data assets, what namespaces, what data items are there? And then when I found them, how do I configure them so that they can be exported to be accessed by these different data access protocols, by these different clients? And if I want to manage these, if I want to say this data should stay in the EU, or this data needs very low latency access and I'm willing to pay for it, or this data requires me to be able to have very high throughput access, etc. All of these bits of information that you want to have sticky, attached to the data you're managing that moves with that data, so that if you move back and forth, you don't have a situation where, well, this worked great here, but it's not working here. Why? Well, you lost all your tunings, you lost all your management directives, you lost all the hints that connect things together. This is the glue that makes this sort of portability possible. And then finally, the transfer. I have data in an environment, I need to move it to another environment. I want to lose as little as possible of the additional information that is attached to that data, so that if I move it back, it's preserved, so that the management information is preserved, etc. These are all really key functions to enable the mobility and portability of data. So why is this valuable? Well, there's three reasons, primary reasons why CDMI has had traction in the industry. The first reason CDMI has had traction is because it's an international, formal, unencumbered, and open standard that anyone can implement, anyone can use. There's a formal specification that describes how it works to provide interoperability. It's had contributors from all of the major storage vendors under SNIA's IP policy, so a lot of the conditions have been thought through, developed, tested, and comes from a wealth of experience across the industry. And SNIA doesn't require licenses, it's open to anyone to implement, and there's a forum where vendors can come and contribute. Most of the technology, most of the functionality in CDMI is the direct result of vendor contributions. They join the Cloud Storage Technical Work Group. They say, I'd like to add this functionality. We collaborate to produce an extension. CDMI's functionality starts out as extensions, and then as we get implementers, it gets added in as an annex to the standard, and then finally gets incorporated into the standard once there's a sufficient level of interoperability demonstrated. So the standard has grown as additional use cases have come forward. But CDMI only requires you to implement the parts you need. So even though CDMI has capabilities as broad and varied as compliance retention and hold, delegated access control, encrypted object access that are really critical in some use cases, it doesn't require you to implement them unless you need them. In fact, one of the jokes we have is that the simplest CDMI server says, no, I don't do anything, but I'm going to tell you I don't do anything. And then you can add on the pieces you need. It's a construction kit for implementing the specific problems that you can't accomplish via other mechanisms. And it's extensible. At every part of CDMI, mechanisms have been put in place so that vendors can add in specific functionality that isn't in the standard without breaking interoperability. Extensible metadata, extensible exports, extensible protocols, etc. And a lot of the vendors bring it to the standards group to add it into the protocol. Vendor extensions are welcomed. CDMI works over all your existing authentication mechanisms. So it doesn't say, oh, you have to go and implement a new way to do things. You use HTTP. You use whichever mechanism you want to authenticate over HTTP. You can use OAuth, you can use BASIC, you can use S3 authentication, etc. It doesn't specify that part. CDMI specifies a representation that you can associate with any URI-accessible object that lets you flip it over and see, here's the management information behind the covers. And finally, it's really simple to use as a client. Many CDMI implementers don't use a client. They use curl. They use the libraries that are part of every language that has rich functionality to talk to HTTP, which is pretty much all of them these days. So unlike a lot of other environments that you have to invest and link in a library and learn a new programming API, if you're doing a GET for a URI, you can do a GET for CDMI just by adding an accept header. It's that simple. So that's resulted in a situation where it's very easy for people to start to use CDMI to just glue pieces together to provide this sideband management channel for their existing systems without invasive, complex changes. So, who's realized value from CDMI? The standard has been around for 14 years. Next year, 2026, will be 15th anniversary of the release of 1.0 of the CDMI standard. Well, one big group that has realized a lot of value from CDMI has been from its long-term interface stability. Multiple governments have standardized or mandate CDMI for long-term digital data preservation. It's an ISO IEC standard. It has that longevity. Similarly, many cross-national scientific organizations have been using CDMI for data interchange and to specify quality of service, to allow different organizations across different countries to be able to exchange data in a standardized way. In addition, many software developers that want a specific feature not supported by a specific data access API have said, well, how do I do this? I can't go and modify NFS. I can't go and modify NVMe over Fabric. I can't modify SQL and do this in a standard, easy way. But with CDMI, I can just add this little side channel for management that meshes with my existing clients. So we've seen a lot of adoption in private cloud instances where they also add CDMI as a means to do bulk movement between clouds. This is either directly in the software or through middleware or proxy systems that will talk native on one side, use CDMI as a transport. So instead of having to have a many-to-many, you need an adapter for every cloud you talk from and every cloud you talk to. You can just convert to CDMI, talk CDMI, and then convert to the destination cloud. Cloud data repositories for AI are starting to bring new use cases. We've had people come and say, Oh, I want to do what CDMI lets me do, but I want an agent to do it. I want to implement this as a piece of my agentic frameworks. I want to use MCP for this. Similarly, I'm starting to deploy these RDMA-based structures. I want to be able to find out how can I access a piece of data. And for AI data sets, how do I provide that self-description, that portability, and manage that movement of data? So we've also heard some complaints over the years. Anything that lasts 14 years and doesn't have some complaints, well, you got to be a little suspicious about that. Probably means it's not being widely used because there's always going to be a diverse set of opinions. So the first big complaint we hear is, I can't really figure out exactly what the goals are and how to use it for specific tasks when I look at the specification. Some quotes. It wasn't clear to me why I would use CDMI until I attended a webinar. And it sure didn't come through when I was reading the spec. Or another one. Oh, I thought CDMI was just an S3 competitor. Totally different layer in the layer cake. And another one. Too often I discover something CDMI does and wish I knew about it earlier. There's so much functionality, but it's often not immediately clear from reading the standard. In addition, while we provided mechanisms to define how CDMI can manage different protocols, in fact, all the way back in the very first version of the CDMI specification, there's a whole section that talked about tables. We didn't provide any examples for this because we were driven by vendors coming in and doing implementations. We waited for them to come, but they were waiting for us to provide an example. Some feedback. I wish the specification was more protocol focused because then I could ignore all the parts that aren't required. Instead of having to fish through and say, oh, well, I have to read through this section because this is connected to this, etc. It would be great if it was really clear. I just need to implement this one section to accomplish this one goal. Similarly, I wish there was guidance to make it easier to add a new protocol to be managed by CDMI. And of course, there's all these minor annoyances in a world that's increasingly used to frictionless software development. The formal specification, which is our strength, is also our weakness. It's long and imposing for people who just want to see an example and use it. The lack of immediately usable examples also has hurt us. And some of the mandates that we specified in the specification. For example, the CDMI specification says, oh, if you want to use IDs, go and get an IANA number, enterprise number. Well, that was fine when it was all the big enterprise storage developers sitting around and saying, yeah, that's reasonable. We all have one of those. Everybody has one of those. But when it's an open source project or a developer trying to connect together middleware, etc., that's a barrier. They have to learn what this is. And then when they find out, they're like, wait, I have to go and talk to a registry and submit and get, this is way too much. I'm going to go find something else. And then we've also had a lot of standardization happen over the intermediate years. A lot of the concepts that we wrote into CDMI are now official RFCs from IETF. Luckily, they've been aligned very well. So it's not like there's one way to do it in CDMI and another way to do it in IETF. But because these RFCs were the focus of standardization in those specific areas, they've done it a lot better than we have. They've covered all of the edge cases. They've formally defined it, and there's libraries out there. So why would we say do A, B, C, D when we can just say use RFC XYZ? And then the implementer can just do a search and say, oh, there's 6 libraries that do this already. I can just use one of those. I know I'm compliant. We're good. And when you're testing, you know, okay, well, the reason why this isn't working is because you're not compliant with this RFC. Much easier on the developer. So why wouldn't we incorporate these in? That could make things a lot easier. And what are the gaps we've heard? Well, there's some emerging workloads and use cases. 3 big use cases. The first one is, I want CDMI to help me find the best way to access data. If I have a data set or a data item, I want a way to say, how can you give me this? What's the fastest way for me to get it? I may have the ability to get it through S3. I may be able to read it through NFS and SMB. I may be able to get it through NFS over RDMA. I want to be able to discover that. But more than that, these things aren't plug and play. When you go to mount an NFS volume, there's a whole bunch of additional information. What's your authentication mechanism? What's your tuning for the highest throughput on that network, etc. Same with SMB, same with these emerging protocols over RDMA. Being able to discover the way to access the data is extremely valuable. And this just doesn't extend to the data access protocol. This also includes when there's multiple representations of the data. One of the big trends with AI is it's not just a picture. It's also a text description of the picture. It's also a vector. It's also extracted metadata tags. It's also a graph, and that graph is in like 3 different formats. So CDMI provides a mechanism by which when you have these multi-representational data, you can discover what representations you can access and how to access those representations. The second big workload we've heard that's new is finding out how data is related. When we introduced metadata into CDMI, that allowed you to attach metadata into any URI-accessible object. But that metadata was specifically scoped to that object. But today everything's relational. Different items relate to each other. People want a standardized way to express that. When you roll your own in metadata, it's limited because there's no standard ontology, no standard mechanism to do that. Unfortunately, we don't have to standardize that because there's already a lot of work done, mature standards there. We can integrate into CDMI to provide this functionality. And third, how does CDMI incorporate into these AI-driven workflows? Well, the first obvious one is MCP, the Model Context Protocol, which has experienced explosive growth over the last 6 months, including many storage companies implementing MCP as a way to discover data, as a way to manage storage systems, and as a way to access that data when you want to incorporate it into your agentic workflows. There's also work being done on how to support new data access protocols like S3 over RDMA, NVMe over UEC, etc. And we've all been hearing about GPU-initiated data access. Well, if you're going to want to access it from the GPU, you need to be able to first know that you can access it from the GPU, and you're going to need to get additional information to connect that together. So that's another gap where CDMI can help out. So, given this, we are now introducing CDMI 3.0. Based on the feedback we've received, suggestions and contributions, the Cloud Storage Technical Work Group has spent much of 2025 identifying a scope of work for CDMI 3.0. This will form the next major revision of the Cloud Data Management Interface. There's 7 new major improvements that we have identified that we will add to CDMI 3.0. The first one is a new MCP representation for CDMI, allowing standardized and open AI-driven dataset management. The second is new guidance for object, query, stream, table, graph, access, data access, and query protocols. The third is adding a new export provided field that dramatically simplifies the work required to discover how to access a piece of data. The fourth, adding a new relations rel field that builds upon web standards to enable graph relationships within and between objects, and to allow new representations, data system metadata for multi-representational data. And of course, we are going to be reorganizing the CDMI specification into 3 parts. The first being an informational introduction to the value of CDMI and how it's used, a normative per protocol section that allows implementers to focus just on the data access protocols that they're interested in, and then a normative per use case section that illustrates how CDMI enables the implementation of common management functionality. And of course, throughout the specification, we will be updating it to bring it into alignment with some of these newer RFCs to help simplify that. And CDMI is an open standard, so if you have challenges in this space and use cases, please bring it to the work group. We always welcome contributors. The standard is built on the input of contributors, and we look forward to hearing what's important for developers and end users in this space. So let's walk through these additions quickly to talk through what each of them are capable. First improvement is adding CDMI over Model Context Protocol. So CDMI is built on RFC 6208. This defines a set of JSON representations that are transported over HTTP. This includes the CDMI object, which is operations on a data item, CDMI container, operations on a data namespace, a collection of items, and CDMI queue, operations on a stream of data. The CDMI specification defines the contents and meanings of these JSON representations. For example, if you wanted to take a snapshot of a namespace, in CDMI, you would perform an HTTP operation. You would perform a patch operation to the path, the URI to that namespace, in this case, CDMI/myfiles. You would specify a content type of application/CDMI container. This is what instructs the server that you're speaking CDMI. Otherwise, it's just standard HTTP. And then you would include in your request body a JSON string saying, I want a new snapshot called my snapshot. So, given that we already have that defined, this slides into MCP very nicely. And the reason is, MCP is based on JSON RPC, a RPC mechanism by which an AI client, the MCP client, can talk to a service provider, the MCP server. So all of the concepts that we've introduced here, the fact that you're wanting to make a change, perform a patch, that you're wanting to do it against the named URI resource, the URI path, that you're indicating that this is a CDMI operation, it's against a CDMI container, and that you have arguments. I want this snapshot named my snapshot. All slides in to the JSON representation defined by the MCP specification and allows the transport of every operation that CDMI supports in a generic and standard way. This is probably one of the cleanest meshings of standards that I've seen in a very long time. We don't have to talk about MCP in most of the standard. We just have to add one section at the top where we talk about here's how CDMI representations work over HTTP, and here's how they work over MCP. And the complexity isn't much more than the diagram of mapping of fields shown here. So let's show a few more examples. What if I want to, for example, go and create a new directory? Well, in CDMI, you do a put to a namespace where you want that directory to come into existence, and you specify some parameters, and you can just leave it default. No parameters if you just want to inherit from the parent, etc. Well, you slide over those same results into MCP. Your function is your putting, you have a CDMI container, and here's your path, and it just works. For example, if you want to get the size of a file, I'm doing a get to a CDMI object, and I want the metadata CDMI size. In your MCP response, the results, metadata, CDMI size, it's a 37-byte file. I didn't have to specify anything to make this work. I just had to specify how the CDMI JSON representation slides in to MCP. If you want to get a listing of files, same thing. I want to list a container. I want to see the children. The result, there comes the children. Very straightforward. So why is this exciting and powerful? Well, everything expressible in CDMI can now be performed by an agent. This means that the combination of MCP plus CDMI provides an agent-driven discovery, access, management, and manipulation of stored data in clouds, on-prem, in a standardized way. They're very well aligned, both JSON-based. They both support capabilities and tool listings for discovery. They both support long-running queries. They both support the concept of routes. They both support the concept of resources. And when connected together, MCP offers some additional enhancements. MCP offers the concept of prompts, templates that you can use. Oh, if you want to create a directory, here's some examples of how to do it. Help the LLM figure out the right way to use it. Here's some listings of what you can do. Here's some ways to discover what functions are possible. And because CDMI is an international standard that has been around for a long time, most of the LLMs out there already know how to speak CDMI. They just need a few additional hints on how to put it into MCP. So this is actually a lot less error prone than when you ask an LLM to use some protocol it's never heard of. You have to teach the LLM how to do that and do it in an ambiguous way. The LLMs today are already trained. CDMI is already part of their knowledge. So when they put things together, their accuracy is already much higher. So we welcome, please come get involved in the standardization of CDMI over MCP and help define AI agent-driven storage management. So the second area is guidance around data access and query protocols. CDMI doesn't define how the data is stored in the cloud. That's up to the cloud company, the cloud software developer. CDMI doesn't define what protocols the clients will use. But CDMI does provide a mechanism by which a management client can instruct the cloud, this data should be exported via this protocol. This data should be exported via this protocol to help connect together. CDMI 2.0 already contains examples of exports for common file block protocols. But we didn't have specific guidance for implementers who wanted to add their own. We assume they come to the technical work group, which many do, but it's great to have examples. And we're going to add sections showing how this is done for not just file and block, but object, stream, and query. The third area, the export discovery. Well, let's say I have a path, and I want to see all the ways I can access that data. Well, we have one field now that's added that lets you find out, regardless of where the export was defined, all of the ways you can access that data. So for example, I may do a GET, and the system will come and tell me, oh, you can access that via NFS v4. And here's the URI you'll use, and here's the version, and it's over TCP/IP, and oh, you need this client, you need the flags hard, and a port, and the specific security configuration. Oh, and you could also access it over SMB. And you need to use 3.1, but you really should use 3.1.1 to get the best performance. And you want to be multi-user, and all your parameters, and you can go through S3 as well. So this provides not just discovery, but configuration. For the fourth area, for adding relationships, we build on the W3 RDF standard, which allows you to specify relationships between resources and within resources using the concept of a subject-object predicate. So for example, if you wanted to have an object and attach metadata that says this particular URI is a presentation, the presentation I'm giving right now in fact, and it has a relationship that the publisher is SNIA.org. And it has a relationship that it's also published by ISO. And the time that it was published is contained within this metadata item. And a description of what that metadata item is for people or LLMs is the creation time of the standard. In CDMI 2.0, there was no way to specify these sorts of relationships between items. By adding this new field, we can create arbitrary type knowledge graph relationships within and between objects in a portable way that can be used to enable many data management applications. For example, this particular set of rel statements creates the following graph. You have the value of the data that's stored with a link to the creation time with a type, this is when it's created. The time, the metadata item has a link to a description describing that in a way an LLM or a person can understand. And the value has two publisher links out to SNIA.org and ISO.org. And because it's CDMI, this is all accessible via MCP. So your LLM can consume this, understand the graph, incorporate it into the answer. The fifth item is adding representations. The simplest example is if I have an image, I might be able to access it as a PNG or a JPEG. But how do I discover that? CDMI provides metadata through the CDMI representations provided, being added, that allows you to discover those representations and allows you to specify a default preferred representation. Finally, there's the reorganization section. We go from the standard today, which goes through and talks about, jumps right into the operations, to a new specification organization that goes and describes the reference model and the use cases, goes through and talks about the different protocols that can be managed using CDMI, and then goes into specific management operations. We believe this will make it a lot easier for people to immediately open the specifications. Oh, I'm interested in CDMI to discover S3 over RDMA. I go to section 5.3.3 and read this. Okay, I know what I need. I have some examples. I have some curl examples. I can make this work, etc. And for the RFC alignment, I won't go through this in detail, but the key RFCs are specifications on JSON pointers, JSON patch, JSON merge, the well-known resource identifiers, which allow CDMI capabilities to be discovered without an additional piece of information telling you where they are, and problem details, which solve a thorny issue, which is when something goes wrong, how do you know when every server responds in a different way? So, a call to action. Are you interested in AI agents and storage management? Join us in the Cloud Storage Technical Work Group to help standardize storage management using MCP. Are you interested in data access protocol discovery and specification? Join us to collaborate on standardizing protocol exports. Are you interested in AI cluster accelerated access to data? Join us to collaborate on discovery of RDMA and scale up, scale out data access methods. Are you interested in knowledge graph annotation of data for management? Join us in collaborating in adding graph relationships to CDMI. So how do you get involved? 3 steps. If your company's not a member of SNIA, you first need to join SNIA. Well worth it. I encourage it. Second, once you're a member, if you're a member, if you don't have an account, you need to create one. And once you have an account, you go into the SNIA members portal and you click to join the Cloud Storage Technical Working Group. Our technical working group, work group meets every week on Friday mornings, and time is split between new contributor-initiated work items and the CDMI 3.0 work items I have discussed today. So let's connect together to work together to connect clouds, data, and AI. So, are there any questions? Go ahead. So the question is the binding between CDMI and MCP complete? Once specified, can all CDMI functionality be accessed through MCP? So the answer is yes. With this mapping, because both protocols are JSON based, because both protocols are document request response based, and because there are clean mappings for the 4 critical pieces of data, operation, URI, data type, and parameters, once specified formally, everything you can do through CDMI, you will be able to do through MCP. And we've already done some examples with widespread LLMs, asking them, here's how an MCP operation is done for CDMI for X. Create me an MCP operation to do Y. And it answers correctly. So that's very positive. Any additional questions? Okay, well, thank you very much for attending. Please don't forget to rate the sessions, and thank you for your time.